Today we're going to start talking about rational functions. So we've talked about polynomial functions in this chapter, we've talked about complex numbers, and now we're going to be talking about rational functions. So first, what is a rational function? Well, a rational function is, as the name suggests, it has the word ratio in it. So it is a function that can be expressed in the form n of x over d of x, where n and d are polynomials, and d is not the zero polynomial. So we're going to be applying what we know about polynomial functions, because now we are, in fact, just looking at the ratio of two polynomial functions, and then that last bit there, d is not the zero polynomial. Now, since a polynomial will never have a square root, our only domain issue is going to be where d of x is equal to 0, so where the denominator will equal 0. Anywhere that the denominator equals 0, we know we have a discontinuity on the graph. Now, in order to analyze a rational function, we will need to know the roots of the numerator and the denominator. So everything we did previously with polynomial functions and finding roots of polynomial functions will also apply here. So before we analyze a rational function, we will always factor the two polynomials if they are not already in factored form. Now, there are a couple of key things that we are going to use to help us analyze rational functions. So first is going to be looking at discontinuities. So you're going to first state the domain. So what are all possible values of x? You'll list any removable discontinuities. So those are holes. And these occur anytime you have a root that is common to both the numerator and the denominator. So anything that is a root in the numerator and is also a root in the denominator. Those are holes. And then once you do that, what we're going to do is we are going to simplify the rational function by canceling out the holes. Now, it is still important to actually list out what the holes are, because that will help us in graphing these rational functions. But simplifying it, getting rid of it, will also help us graph the general shape of the function. Now, once you've done this, and now you have your simplified rational function, we are going to apply this. Really, we're just applying and finding a number of different things. But to help us remember all the different things we're going to find, we are going to use this term rat2e. Now, a lot of people find it helpful to remember it because it almost sounds like ratatouille. It's not quite, but if it helps you to remember the different pieces of the function that will help us with graphing, you can do that. So R stands for roots, or in other words, the zeros or the x-intercept, and these occur at roots of the numerator. So anything that makes the numerator equal 0 will be a root. It will be an x-intercept. Next, the A stands for asymptotes. In particular, we're looking for vertical asymptotes. These occur at roots of the denominator. So anything that makes the denominator equal to 0 will be a vertical asymptote. Why? Well, because vertical asymptotes, if you'll recall, are places where the graph gets very, very close to but never actually reaches. The reason it never actually reaches is because these are the values which make the denominator equal to 0, and we know that the denominator can't equal 0. But we can analyze what happens as it gets very, very close to 0. All right, the t with the 2, there are two t's, and the first one is tangency. So tangency, you'll remember we talked about polynomial functions, and when it's tangent at a root, that means it will bounce. And so anytime there's a root in the numerator with a multiplicity of 2, the graph will bounce, or the graph will be tangent at that point. It will just touch and then go back to either being in the positive side or being back on the negative side. So depending on where it's coming from, it will go back to where it came from. The second T stands for togetherness. Now, togetherness refers to where the graph comes together at a vertical asymptote. Now this occurs at roots of the denominator that have a multiplicity of 2. Now remember that anywhere that you have a root in the denominator, all right, so if there's something in the denominator that makes the denominator equal 0, we already know there's a vertical asymptote there. And so what the multiplicity of 2 tells us is that from either side of that asymptote, the graph is going to go in the same direction. So either from both sides, it will both be going down, closer and closer to the vertical asymptote, or it might be going up on both sides as it gets closer and closer to the vertical asymptote. But in other words, togetherness means the graph is going to be coming together in the same direction, closer and closer to the asymptote, but they won't be going in opposite directions. All right, the E stands for end behavior. End behavior, you have to compare the degrees of the numerator and the denominator in order to determine what's happening. So end behavior, remember, refers to what is happening on the far ends of the graph. Another way to think of this is, what does the graph look like if you were to zoom out really, really far? What does it look really, really close to? Does it look like a line? Does it look like a horizontal line, maybe a slanted line with some sort of slope? And so the way we figure out what this end behavior is we have to compare the degrees of the numerator and the denominator. Now, if the degrees are the same, then the horizontal asymptote is at y equals the leading coefficient of the numerator divided by the leading coefficient of the denominator. So this means that whatever that might be, y equals, this should be some sort of constant because it's a leading coefficient divided by leading coefficient. It should be a constant number here. But essentially, if the degrees are the same, and if you were to zoom out from the graph, it would look a lot like this line, y equals whatever the constant is. It will just look like that line, that horizontal line. Now, if the degree of the numerator is smaller than the degree of the denominator, then you have a horizontal asymptote at y equals 0. So no calculation needed. You just know that the horizontal asymptote is at y equals 0. If you were to zoom out really far, for any case where the degree of the numerator is smaller than the denominator, if you zoom out really far, you'll end up with just a horizontal line right along the x-axis. And then lastly, if the degree of the numerator is greater than the degree of the denominator, then this is going to have what we call a slant asymptote. So in order to figure out what that slant asymptote is, you are going to have to do some division. Now, depending on the problem, you might be able to do synthetic division. You might have to do long division. Either way, whatever you get for the quotient, you ignore the remainder. Whatever you get for the quotient is going to help you determine what that line, that slant asymptote line is. So let's say you end up with y equals 2x. Say the quotient is 2x. Then you would draw a line at y equals 2x, and that would be what we call a slant asymptote. And so the graph will get very, very close to this line, but never actually touch it. And if you were to zoom out, it's going to look a lot more and more like that line. So that's end behavior. The y at the end is going to refer to the y-intercept, and this occurs when x is equal to 0. So simply, you would plug in 0 for x, and then whatever you get for y is going to be your y-intercept. Okay, let's do 2 examples together. We're going to start by doing the analysis first, and then once we have finished the analysis, then we'll go ahead and put all that information onto the graph and help us graph the rational function with all that information. So here's the first one. X minus 3 times x plus 2 squared, all over x minus 2 and x plus 1. So first, let's talk about the domain. So the domain is all real numbers except for what makes the denominator equal 0. In this case, that would be 2 and negative 1. So all real numbers except for 2 and negative 1. All right, next we want to check for any wholes. So anything that is common to both the numerator and the denominator. We don't have anything in this case, so none. And now, since there were no wholes, there was nothing for us to simplify or cancel out, we can begin the Ratatouille part of our analysis. So R stands for roots. So the roots are anything that makes the numerator equal to 0. So that would be 3 and negative 2. Next we have asymptotes. In particular, we're talking about vertical asymptotes, which are anything that makes the denominator equal to 0. So that would be at 2 and at negative 1. All right, now let's talk about tangency and then togetherness. So tangency, you're looking for anything in the numerator that has a multiplicity of 2. In this case, the x plus 2 is squared, so we have tangency at x equals negative 2. That means that the root, being at negative 2, means it will touch the x-axis at negative 2, but instead of going through, it's going to bounce off of it. Now, in terms of togetherness, we're looking for anything in the denominator that has a multiplicity of 2. We don't have anything in this case, so we'll just say there's none. Now let's talk about end behavior. So the end behavior, you have to compare the degree of the numerator with the degree of the denominator. Now since it's already in factored form and you want to compare the degrees, you want to add the multiplicities. So in the numerator, we have a degree of 3, and in the denominator, we have a degree of 2. Now since the degree of the numerator is larger than the degree of the denominator, we're going to have to divide because we have a slant asymptote. Whatever we get for our quotient from dividing is going to be the slant asymptote. So if we're trying to divide this, we might want to actually have this all multiplied out. So multiplying out the numerator and multiplying out the denominator, this is what we have. And we're going to have to divide. Now, since the denominator is not in linear form, we're going to do long division. Now, you can also opt to just multiply out the numerator, and then you could do synthetic division twice with 2 and then with negative 1. That's fine. I'm going to go ahead and do the long division here. So doing long division, we have, we have x up here. Multiply that, we have x cubed minus x squared minus 2x. Subtract, and this comes out to be 2x squared minus 6x, bring down the minus 12. Apply division again, so we have positive 2 up on top. Multiply, we have 2x squared minus 2x minus 4. Subtract, and we have minus 4x minus 8. There's nothing else to bring down. The degree of the negative 4x minus 8 is smaller than the degree of x squared minus x minus 2. So the negative 4x minus 8 is the remainder. Remember, we don't need to worry about the remainder when we're talking about the slant asymptote. And so our slant asymptote is simply going to be y equals x plus 2. All right, lastly, we are going to figure out what the y-intercept is. And so this is when x equals 0. And so you can plug 0 right into the rational function. And this will give us negative 12 over negative 2, which is equal to positive 6. So we have a y-intercept at 6. All right, now let's take all that information and let's go ahead and put it into a graph. Alright, so we said that we have roots at 3 and at -2. So I'll put those points there. We know we have vertical asymptotes at 2 and at -1. Draw those in. And now what I like to draw in next is the end behavior. The end behavior tells you what's going on at the far left and far right of the graph. Now our end behavior was a slant asymptote, y equals x plus 2. So I'm going to draw in that line. So that's a line with a y-intercept of 2 and a slope of 1. Now you'll notice this goes through -2. That's fine. With vertical asymptotes, you absolutely cannot touch in terms of the graph will never actually go through vertical asymptotes. But the horizontal asymptote or the slant asymptote, it's an end behavior. So it's really just telling you what the graph looks like at the far ends of the graph. So if you were to zoom out really, really far, this graph would look like this line that we've just drawn, the slant asymptote y equals x plus 2. Okay, so we also know that the y-intercept is at 6. So we'll put that in as well. Now notice here that this kind of middle portion where the y-intercept is at 6, we can kind of fill that in. Remember that the graph is going to get very, very close to the vertical asymptotes on either side, but never actually touch. Also know that the other thing that we learned is that there is tangency at -2. That means that it's going to just touch -2 and then go right back. Now, if you're ever unsure of what the general shape of the graph looks like, you can always plug in more points, more values of x to get another value of y. So for example, let's say you weren't sure what happens past -2 on the left. Say you plug in -6. You can plug -6 right into the rational function and get a value for y, and that will give you a good idea of another point and hopefully help you draw in the function. Now, the more that you do these, probably the less that you'll have to rely on using more points. Now, because you know there's no togetherness, you also know that at the vertical asymptotes, if on one side of the vertical asymptote the graph is going down towards -infinity, then on the other side of the vertical asymptote, it will be going the opposite direction towards +infinity. So here's the graph. Here's this portion here on the left. It goes to -2, it touches, and then it bounces right off. And then it goes towards -infinity as you get closer and closer to that vertical asymptote at -1. Now, since you know it goes towards -infinity as you get closer and closer to -1, you know on the other side of the vertical asymptote at -1, it's going to be going up towards +infinity. So now we can draw in this second portion here. And then since you have this second portion here going up towards +infinity next to x equals 2, that vertical asymptote, you also know that on the other side of that vertical asymptote, it's going to be going in the opposite direction, right? There's no togetherness. So it's going to get very, very close to -infinity on the right-hand side of the vertical asymptote, and then it's going to go through 3. There's no tangency at 3, so it will just go straight through 3, and then it will get closer and closer to that slant asymptote because the end behavior looks a lot like that line, y equals x plus 2. And there's our graph. Okay, let's look at example 2. Analyze and sketch a graph of f of x equals 2x squared plus 10x plus 12 over x squared plus 3x plus 2. Now this one is not in factored form, so we can start by factoring it. Now the denominator is pretty easy to factor, just x plus 1 and x plus 2. In the numerator, we can factor out a 2 first, leaving us with x squared plus 5x plus 6, which then can be factored to x plus 2, x plus 3. All right, let's start the analysis. So the domain is all real numbers except for what makes the denominator equal 0, which would be -1 and -2. As you can see here, I've canceled out the x plus 2's, which means there's a hole at x equals -2. Now, we are going to have to graph that hole when we get to the graphing portion. And so in order to figure out where that hole is, after you've canceled out the x plus 2, you can then plug in -2 back into the function. So 2 times -2 plus 3 over -2 plus 1, and that will give you your y value. That comes out to be 2 times +1 over -1, and so that's going to be equal to -2. All right, let's start the rest of the analysis now that we've simplified our rational function here. So are the roots anything that makes the numerator equal to 0? That would be at -3. Now, again, we're looking at the simplified rational function. For vertical asymptotes, we're looking in the denominator, and that looks like x equals -1 makes the denominator equal 0. For tangency, we're looking for anything with a multiplicity of 2. Doesn't look like we have any. And then for togetherness, we're looking in the denominator for anything with a multiplicity of 2, and it doesn't look like we have any. Now, anytime we get this information, it always seems like, well, that's not information, but it is. Knowing that there's no tangency means that at x equals -3, it's going to go right through. Knowing that there's no togetherness, that means that x equals -1, the graph will be going in opposite directions, coming from the left versus coming from the right. Okay, now end behavior. Compare the degree of the numerator and the denominator, and we notice here that they are the same. So when they're the same, you divide the leading coefficient of the numerator divided by the leading coefficient of the denominator, so that would be 2 over 1. So y equals 2. And then lastly, the y-intercept is when x equals 0. Plugging 0 in, we end up with 6 over 1, which is equal to 6. Okay, now let's put in everything we know. We have a root at -3. We have a vertical asymptote at -1. No tangency, no togetherness for us to draw in here. Look at end behavior. So the end behavior, meaning at the far ends of the graph, this will look a lot like the line y equals 2. So that's a horizontal line. So we can draw a horizontal asymptote there. We also have a y-intercept at 6. Okay, so you know at the far ends of the graph what this is going to look like. It's going to look like that line y equals 2. So if you start on the far left and you sort of imagine that you're really, really close to the line y equals 2, and then you still have to get to -3. So it's going to come off of that horizontal line until it gets to -3. And then because there's no tangency, it's going to go right through -3 and then get very, very close to the vertical asymptote. And on the other side, you are going to start at positive infinity on the other side of the vertical asymptote because there's no togetherness. That must mean that is coming from the opposite side. Go through +6, the y-intercept, and then get very, very close to the line y equals 2 because the end behavior looks a lot like that line y equals 2. Now the last thing we have to put into our graph is the whole. So we said the whole is at -2, -2. So we're going to find -2, -2 on our graph here, and we're going to draw in our whole right there.